Okay, let's begin. Hi, everyone. My name is Aditya. I will be your instructor for the next 2 hours on a class that delves primarily in deep learning architectures. So we'll be talking about machine learning, we'll be talking about deep learning, and more specifically, we'll be talking about what deep learning is. We'll talk about different ways you see deep learning in today's world. And most importantly of all, we'll be talking about the architectures of deep learning. So how we have deep learning models, how they work, the intricacies surrounding them, how they train, and yeah, cool stuff. I think it's fun. A little bit about me. My name is Aditya. I'm a senior, incoming senior at UC Berkeley, studying physics and computer science. Uh, yeah, like I just really like machine learning. That's where my research is. That's where like I spend most of my free time doing. So yeah, I think it's really cool. Really excited to share that with you. So without further ado, let's just dive right in. Structure. Let's talk about the structure. We'll be talking about the foundations of machine learning. So, what constitutes machine learning? What's deep learning? We'll be talking about neural networks, which is the cornerstone of deep learning. That's essentially what deep learning is. Then we'll move on to the simplest form of deep learning, which is a multi-layer perceptron. If the name worries you, then don't be. Uh, Someone asked me to start an AI companion. I'm not sure what that is. I'm not very Zoom savvy, sadly. So I trust that you'll be using this well, I guess. Uh, but yeah, at any rate, so we'll be talking about MLPs, which are the simplest form of neural networks. Then we'll move on to something a bit more complex, which is a convolutional neural network, a CNN. Finally, we'll move on to transformers, which are probably the most user-facing side of machine learning that we have in today's world through generative AI. And yeah, through that we'll be talking about dimensionality reduction, and finally we'll talk about synthesis. Breaks. We'll have one between, I think, MLPs and CNNs. I don't MLPs and transformers, my bad for that. But we can have as many as you want. I'll ask periodically if you're comfortable with the content and if you want to take a break to rest your mind or whatever. Uh, cool. So that's housekeeping out of the way. Okay. Do we have any new participants? No, all good. Okay, so let's jump into the foundations of deep learning. Right. Oh, also one more thing. If you have questions, you can raise your hand virtually via Zoom. And yeah, I might answer those questions maybe after the next slides, but I'll be sure to get to your questions. Or you could post them in chat, and I'll be reading chat periodically. And yeah, I'll be answering questions from there as well. So yeah, either way works. Cool. Audio doesn't work. That's okay. You can use chat to answer questions. And cool. I'm not sure if I can. Oops, going a bit too far, too soon. I'm not sure how that works, but yeah, like if you can get it to work, then like I gave you permission. I'm not sure if I'm allowed to though. Cool. Before machine learning, let's talk about biology. I'm not a biology student. But I do think that it's fairly relevant because probably the most effective form of learning outside machines in the world right now is our human brain. It might not feel like it sometimes, but that's true. Brains can learn anything. Brains are very adaptable. So a bunch of really smart people in the 1960s and 70s thought that if we can emulate a human brain on a computer, well, we have essentially a really good system for a machine. Right, because our brains are really effective. Now, brains, studying the structure of brains, that tells us a brain is made of a neuron. Neurons are tiny cells that are connected to each other, and they can turn on and off. Now, if a neuron turns on and off, the neuron's neighbors are also influenced by that decision, and they can also turn on or off, depending on whether the original neuron turned on or off. That's a simplification. There's a lot of things going on. There's like synapses, axons, there's chemical bondings that I'm glossing over, but that's the general premise of a neuron. So The idea is, what if we make our computer simulate a human brain structure? And on principle, it's a good idea because, the brains are really good. Like they are a proven architecture, they reliably learn, they adapt. And so yeah, that's a given point. There's also the point of generalization. Brains can learn almost anything. Like I could swap gears right now and teach you chemistry, and you'll be disappointed, but you'll still be learning. So yeah, they can generalize. They have layered processing, which is a bit more subtle as a point. And that's to deal with how brains process data. So, for example, if I'm reading a book or I'm looking at the slide, then the data from the slide goes through my eyes, passes through my retina, goes through my nervous system, enters my brain, and it processes itself in my brain. Machines also learn in a similar way. They take data, they pass it through their pathways, and then they finally store it in their neurons, as we'll get to. So they have layered processing, so there's a
Yeah.
similarity there. And so yeah, like having a similar processing system makes things easier. Cons of the system, there's a lot, but the most important thing is brains are incredibly complex, and we can't simulate them on computers. We don't know how learning works, we don't know where memories are stored, so yeah, it's difficult. So we move to a middle ground, which is deep learning. Now, deep learning is essentially a simplification of the brain. It does the same things that brain do, but in code. It builds layers of artificial neurons that pass signals, adjust connections, and it learns on prior experiences. So if we provide data to our brain, we learn. If we provide data to our code, it also learns. So neurons are inspired by brain, trained by data, powered by math. I think that's a cool science catchphrase. Will we actually make our computer simulate a human brain structure? Not exactly, but we will be simulating it. So let's talk about the simplest form of deep learning, which is the neuron. In the simplest possible terms, a neuron is something that takes in an input, does some math on the input, and provides an output. That's about as simple as you can get when you're explaining a neuron. So it takes an input, it does some processing, and it spits out an output, and the output is closer to what we want than what the input was. So let's concretize this a little bit. Let's talk about what is an input and what is an output. So, so the input of a neuron is mostly a number. It can be any number, like from negative infinity to infinity, and then you do some math on it, and it gives an output, which for our purposes will be a number between 0 and 1. And it could be any number technically at the output, and often is any number, but for everything we're doing today, the output is between 0 and 1. So to recap, input is a number. And it's a number that we don't really care for all that much. We do some math on that number, and it gives an output, which is something we want. The key point of a neuron here, though, is that neuron can take multiple inputs, just like a human brain, where one neuron can be connected to many other neurons, but fires only once. A neuron can accept many inputs. It can take as many inputs as you want. It can take in as many numbers, but it only has one output value. So it does the math on input 1, input 2, input 3, and the output then becomes a function of input 1, input 2, and input 3. If you know what functions are, if you know mathematics, that this should make sense. Uh, but if you don't, like, I'm not assuming any mathematical knowledge, so I'll give you an analogy for this. I like to think of neurons as jurors in court cases. So, jurors in courts often take in evidence, they parse the evidence, they think about the evidence, and based on that evidence, they come to a conclusion of whether the defendant is innocent or guilty. So, a neuron works in a similar way. The inputs it takes are different pieces of evidence. For example, if you're doing a bank robbery, if the money is missing, then that's a pretty strong piece of evidence. And then the neuron parses that evidence, and it comes to a conclusion of whether the defendant is innocent or guilty. whether based on the evidence, the output should be 0, which is innocent, or 1, which is guilty, or anything in the middle on how confident the juror is. So if the output is 0.5, then there's a 50% chance that the juror thinks that the person is guilty. So let's concretize this again. I'm going to delve into some math here for the next slides. I'm sorry for that if you are not really comfortable with that. But I think this is important because yeah, neurons really form literally all of deep learning. So you should have a good idea here. So uh, each juror in a court case, he has his own perspective on what constitutes important evidence and what constitutes unimportant evidence. Right. So if, for example, if the money is missing in a bank robbery, then that's really important evidence. But let's say if a balance sheet was missing or like some other thing was like completely in the wrong place, then that's not really that important. So I take each piece of evidence and I weigh it by what I consider important or not important. So if I consider it important, then my weight for that piece of evidence will be high. If I don't consider it important, then the weight will be low. And it makes sense that if I have a high weight for a certain piece of evidence, so if I have a high weight for an input, then the output should be directly proportional to that higher weight and that input by correspondence.
Was there. I
So,
wonder if she's sitting there because Trisha usually sits in this chair doing something.
sorry, I didn't quite catch that. I apologize.
Oh, you heading out?
I think you're
I'm
unmuted.
gonna
Just
go help Dad with something.
I'm just going to mute you. Okay. My bad. Okay. Cool. So yeah, if I have a certain if my input is important, if my evidence is important, then my weight should be higher for that, and that means that my output should also be higher. So essentially what I'm doing is I'm doing a weighted sum of all evidences of all inputs. And finally, before I come to a conclusion, I also take into account my own bias. If I'm a juror, I know I have a bias in a court case, like every human has bias in there. So I take the sum of weighted inputs, I add my own bias to acknowledge the fact that, yes, like I could have influenced my output. I could have pronounced a guilty verdict when he's not necessarily guilty. So yeah, I add my own bias in there. Over the sum of weighted inputs, and my output should be roughly in that range. So now we are making a decision. If we have evidence 1, input 1, evidence 2, input 2, and evidence 3, input 3, then we do a weighted sum of the
Hello.
inputs. We add our bias, and we finally have a number. The only problem is that this number is not between 0 and 1. It doesn't have to be, like no one told it to be between 0 and 1. Uh, what does bias mean? Uh, Bias is, we'll get to the mathematical term, but for now, it's just an offset. So if I say a bias, then whatever sum I have over here, like let's say I have the sum of the weighted inputs is 10, then I'm going to, and my bias is 1, then I'm going to add 1 to this sum of weighted inputs. So it's going to be 10 plus 1. So my output will be 11. So the bias is some fixed number that we add to whatever we get over here. And that number is always fixed. We'll always add this number to the sum of weighted inputs over here. Hope that clears that up.
Excuse me.
So, sorry, go ahead.
If the model is trying to make a decision, then it would need a particular threshold, right?
Yes. And that's where we get to activation. And that's what makes deep learning deep. Otherwise, there's no concept. Like you can just have this, and this is a linear model. Essentially, like the more input you have, the higher your output gets. But that's not how it is in real life, right? Like you cannot, if you reach infinity through an output, then there's not much use in that. So we'll be talking about activation now. To get a decision, to get an output over here, we take this weight times input plus bias, and we scale it by this activation function where sigma, our activation function, scales everything to be between 0 and 1. Now, that doesn't make sense. Let's go look at the math a little bit. So for our particular neuron, we have three inputs and one output. So we have x1, x2, and x3, which correspond to input 1, input 2, and input 3. We multiply them by their corresponding weights to get w1, x1, w2, x2, w3, x3. We add a bias in here, and that's our output without activation. Now let's say this result came out to be +4. Then I pass it through this activation function. So this is my activation function. I look for +4 on the x-axis, and I find the corresponding y value. So that's somewhere really close to 1, which means that if this weighted sum plus bias gives me a value of +4, then it's very likely that my output is close to 1, and that means that the defendant is guilty. Likewise, if I got -4 for this sum, then the output value for the sigmoid would be very close to 0, which means that the defendant is not guilty. So that's how we're making decisions through a neuron. So if we put, let's say, a threshold cutoff of like, if this sum is 0, then there's a 50% chance my defendant is guilty, 50% chance my defendant is not guilty, then we can't really make decisions. But less than that, my defendant is innocent. More than that, my defendant is guilty. So hope that answers your question. And yeah, generally, you don't have to have just 3 inputs. You can have any number of inputs. So I just chose 3 here because it looks good. And yeah, if you know summation notation, if you know mathematics beyond like, I don't know, AP algebra, then you should be good with this. But again, you don't have to know this. All you have to know at this point is neuron takes in many inputs. It takes the weighted sum of the inputs. Then it adds its own bias. So the bias of the neuron is constant for that neuron. And it adds that bias to the sum. And then it scales that sum down to be between 0 and 1 using an activation function. So do we have any questions? Over here. If my weighted sum is, let's say, between -4 to -6, always, then I'm always going to get a value of 0. Right, if that makes sense. So if I have, let's say, w1 x1 plus w2 x2 plus w3 x3 is always going to be between -4 and -6, then I'm always going to be not guilty. And I'm always going to give an output of 0. I see, you want the literal definition of bias. The literal definition of bias is, actually, I don't remember, but typically what we mean by bias is a prejudice or an inclination either for or against definition of bias. And yeah, that translates well into the math definition. Anushka has asked if neurons output is a confidence value and it's getting input from other neurons, does that mean that the inputs to the neurons are also confidence values? Yes, actually, when we get to our first neural network, we'll be talking about that. They're called feed-forward neural networks. And what that means is you're feeding the output of one neuron into the input of the other neuron. And that's actually how deep learning actually learns, because you progressively build on the inputs of previous neurons to get better and better and to capture different things about your data. So yes, to answer your question. Okay, does anyone have any other questions? Okay, I think we're good. So, just to be sure, everyone is okay with this, right? Like, please tell me if I'm not doing a good job explaining or like I'm going too fast or too slow. Just let me know in the chat. Okay, so we have neurons. Let's put them together. Like, that's the whole point of this, right? But why do we want to put them together? Well, the thing is, the problem with neurons is one neuron is too simple. If we are to make cool stuff, if you're trying to make generative AI, if you're trying to make prediction models, then we have to consider the fact that one neuron cannot represent the real world. There's also the fact that real world data is messy. It's not perfect. So if I pass in non-perfect data into a neuron, it's too prone to errors. It can make mistakes because it's only learning from there. And finally, the output is only black and white. In my juror example, what if I didn't want to check innocent or guilt? What if I wanted to check which laws were broken? So if my output is not binary, then yeah, the simple single output model does not work. So we move to a layered system, where a layer is essentially just a bunch of neurons that are stacked vertically on top of each other. Why is that good? Well, because one, it's more complex, so it can model things more effectively. But it's also understandable because it's manageable levels of complexity, so we know what's going on. It's not complete chaos. We're not just throwing neurons randomly at problems. So, I see someone has joined, right? Yes, so it simplifies the math. It also has visual intuition because we can see layers. And that's really important because if we see layers, then yeah, it just makes things easier, and you'll see why. And finally, more neurons equals teamwork. So yeah, like if one neuron makes a mistake, other neurons can work to mitigate that while the model is training. We'll get to that in a while, so don't worry if that doesn't follow. So now we move on to the simplest form of deep learning, which is the multi-layer perceptron. Now, the name is fancy. The name is very fancy. It has multiple layers, hence the multi-layer. So there's the input layer, layer 1, layer 2, and output. And perceptron. So perceptron is simply a neuron over here. So this connection of neurons is called a perceptron. And again, this isn't on the test. You don't have to know what a perceptron is. The actual definition is a bit messier than that. But all it is it's taking an input, it's passing it through successive neurons, where the output of one neuron becomes the input of another neuron, as I think Anushka had asked. So yeah, confidence intervals on confidence intervals. So we are passing in data from the input through to the layer 1. The layer 1 has an output that passes to layer 2. Then layer 2 has an output that passes to layer 3. And layer 3 is the processes the data to create the output. So yeah, this is the general concept. But again, each layer only has one neuron. That's not very good, right? Like when I showed the picture of layers, I showed like 4 neurons in one layer. So let's think in 2 dimensions. We achieve a significant step up in complexity, but fundamentally it's the same thing. So we have input, and the input layer passes data to the first layer. The first layer processes the data and passes its output as the input to the second layer. The second layer processes this input and passes in its output as the input to this final layer. And the output of this final layer is the actual output of what we want. So again, this might seem intimidating, this might seem off-putting, the number of arrows, what's going on. So yeah, let's zoom in onto, let's say, this neuron, this particular neuron. So let's consider this neuron in red, and let's consider the connections it has. So the neuron takes input from the input layer. So it takes an input from the 2 neurons over here. So we have the first connection and the second connection. And the neuron then processes these 2 inputs using the techniques that we just described. And it passes its output to all 3 neurons in the next layer. So it passes its output to this neuron, passes its output to this neuron, and passes its output to this neuron. And that means that this neuron in layer 1 is connected to every neuron in the previous layer and every neuron in the next layer. This is important. Every neuron in a certain layer is connected to all neurons in the previous layer and all neurons in the next layer. So for example, if we consider this neuron is fully connected to the input layer, so through these connections, and fully connected to the output layer to these connections. So that's all that's happening. The number of arrows here simply represents the fact that every layer is fully connected to the input to the previous layer and fully connected to the next layer. And we can see the same thing happening for layer 2. So now that we have this idea, let's talk about forwarding data. So let's say we have some data x1 and x2. That passes into the neuron. It passes into the neuron as input. The neuron has its own bias over here, as we discussed. So it does the processing, it does the summation, and it passes its output, whatever it got, into this neuron, and this neuron. And the output is scaled by W3 for this neuron, scaled by W4, weight 4, for this neuron, and scaled by W5, or weight 5, for this neuron. So even though we are sending the same output, it's getting sending the same output to different neurons in the same layer. Each output is getting scaled by a different value, and that's what makes an MLP special. Even though each neuron gets the same data, fundamentally, it's weighted differently because each neuron thinks about that data differently. So it can capture different parts of the same data. So it can do analysis on the same data in different ways. Let's formalize this. Let's put this down. So our first neuron has an output O, and that's calculated by, we take the weighted sum of the inputs. So that's x1 plus x2, and that's weighted by W1. So W1 x1 and W2 x2. So, and then we add the neuron's bias. Finally, we scale all this with a sigmoid function to make sure it's between 0 and 1. Now, this output O then becomes the input for this neuron, and this neuron, and this neuron. So for this neuron, we get the output. For this neuron, we have W3 into O. For this neuron, we have W4 into O, and W5 into O for this neuron. So we see that each neuron in the next layer gets the same output, but it's weighted differently. So once our red neuron computes its activation, it doesn't send a single signal, it fans out. Each outgoing connection multiplies the output by its own weight, and those products become the inputs for the next layer's neurons, which then add their own bias and then squash the value to be between 0 and 1 through their own sigma. So in this way, a single neuron's output influences every other neuron downstream. And this is important because this allows us to build on our models. This allows us to ensure that having one layer and then having a one layer learn something means that the other layer builds on that. It doesn't start from scratch. Okay, that was fairly heavy. Questions? What preliminary info do you need to learn this better? I'm sorry, I didn't see a question before. Preliminary info, I guess an introduction in math would be linear algebra is really useful for this. If you don't have that, that's fine. I've tried my level best to keep this as math free as possible, but there is always some math to be done in machine learning. And your next question is, what are the layers? Layers are just collections of neurons. So if we go back, then this is layer 1. This is layer 1, and this is layer 2. And all layers are connected to their previous layer and to their next layer. Okay. Equation of the sigmoid function, heard of the sigma function. Right. The equation of the sigmoid function is slightly beyond the scope of this class, but I'll still put it up. So just a second. It seems my screen went missing. Okay. So the sigmoid function is, oops, I'm trying writing with a laser pointer. That's not good. Okay. So the sigmoid function is sigma of x equals 1 over 1 plus e to the negative x. And this does what we call a ramp. So it looks like this around x equals 0. And yeah, I've shown you the picture, and what it does is it compresses no matter what x value you have, the y value will always be between 0 and 1. And this is good for many reasons. One of them being that, again, you don't have infinities, which are generally bad. And yeah, like one, it's fairly easy to interpret. One means absolute certainty, 0 means absolute uncertainty. So how does neuron dropout work, and like how does it prevent overfitting? Dropout is a slightly more complex concept, but what it means is in a certain layer, we only consider, let's say, 80% of the neurons, and we only pass the input of 80% of the neurons to the next layer. And the reason for that is because sometimes neurons can overfit. A single neuron is always prone to making errors, right? Like as I talked about, if I get bad data, if I happen to pass some bad data into a single neuron, then it might generalize to that, which is not what we want. So if we randomly drop out some layers, then we are more likely to get neurons that work. If that makes any sense. By the way, why sigmoid function? It could be any function. There are many functions. There's something called the rectified linear unit. There's exponential linear units. There's the hyperbolic tangent function. Like there's many of them. For this class, I'm using sigmoid because I think sigmoid is easier to explain. But yeah, like you can have almost like there's so many functions that you can do. The world is your oyster for that. Okay, for the last neuron, how does it make an output to how does its output translate to making a decision in a real life setting, since its output is just one number? Well, yes, see, so the model I chose was for education purposes only, like in real life. And actually, I'll be doing an MLP demo, I think, if we have time, then like to show you how easy it is to code an MLP from scratch. Uh, and there we'll have three outputs, one for each class of what we want to predict. So yes, like this is way too simple. So yes. Is there a way to intentionally drop neurons that are bad, like based on their accuracy on the training data? Well, yes, you can, but it's not recommended because that's creating the same problem that you're trying to avoid of overfitting. So if you drop neurons based on the training data, you don't know if the training data was bad or not. So yeah, like you can't trust that. You want to be as general as possible. Okay, I think, yeah, I'll stop there. The questions are getting a bit advanced and I haven't got there yet. So, yeah, so all I want you to know right now is that each layer in an MLP is fully connected to all previous layers and fully connected to all subsequent layers. Okay. But how do we learn? There's no learning so far in what I've described. I've just described the structure, right? How do we know that once we pass in an input, we magically get the right output? Because yes, I have the structure of the model, but that's not doing anything, right now. So now I want you to think about what it is that we are actually passing our data through. The model. Let's talk about the weights that I was talking about here. The inputs are weighted by a certain weight for each neuron, and these weights are unique to each connection. So this red neuron has a weight that goes to this neuron, and it is proportional, and it's unique. So there's no other connection that uses W3. W3 is the weight that is only used by this neuron and this neuron in their connection. So there are many weights because there are many connections. How do we know them? And consequently, how do we know the bias for each neuron? Well, we don't, right? We learn them. Like, no, I don't think God gave us weights for any MLP problem. So if God gave us weights, though, with perfect weights, any input could be transformed into the right output, provided we have a model of sufficient complexity. So how do we train? Well, before that, I'd like to tell you one golden rule. If you take away nothing else from this class, take away this. Everything is numbers. every data that you can think of, every piece of data, every word, every action, all of it can be translated into a number. And that's what makes machines so powerful. You can transform everything to ones, zeros, and everything in between, and use that as inputs for your machine model. So we have our data. If we can convert something to numbers, we can pass it through an ML model, and we can train the ML model on it. But how do we train an ML model? So let's talk about loss. Okay, so for an ML model, the way it works is we pass in our input, and that input gets passed to subsequent layers, and finally gets transformed into the output that we want. Right, sorry. My bad. Yeah, I kind of lost the yeah, I lost the Zoom link, my bad. Okay. Right. So if we have a model that we pass our data through, then our model makes a prediction by passing inputs and getting an output. Kind of like a student who takes a quiz, like you learn for a test and then you just like answer questions on the test and then finally you get a score on the test. Now, if you got a good score, then you did well. If you got a bad score, you did badly. Same thing for a machine learning model. We compute loss, how far the answer was from the actual expected answer. So it's like giving a model a test, saying that here's some data, learn it, give an output, and we'll compare your output to what we think the output should be. And if you got the same output then as what we expected, then that's a good thing. If you didn't, well, try better. So we tried to minimize our loss, with our loss being how far the answer was. So the larger the red lines here, the more the loss. This is something I picked up from a previous class. You don't really have to worry about that. The loss function is an important characteristic now, though. So imagine I have a weight. Let's say I'm trying to find W1. One thing I could do is vary the value of W1, and for each value of W1, I could check how good my result is. So if, for example, a value of 0 for W1 gives me the correct answer, but the value of -1 for W1 gives me the wrong answer, then I'll say that 0 is better and the value of W1 should be 0, if that makes sense. And again, W1 could be any value between like -infinity to infinity. So what I want to do is I want to test the value of W1 at every single point, theoretically. I would like to test this at every single point and come up with a value that minimizes my wrong answers. And that testing, that varying, is what we call the loss function. So we vary the value of the parameter, and we try to see how good or how bad the model is. And we try to quantify that by the loss, so how far the model is from the actual expected answer. And we can do this for one parameter, in which case we plot loss on the y-axis, and then it becomes a 2D plot. Same thing we can do for two parameters, in which case loss becomes a three-dimensional plot. So we have two parameters on the y-axis, x-axis, x and y-axis, and we have loss on the z-axis. So we have a conceptual understanding of loss. But there's a lot of parameters in a machine learning model. In the simple, small, tiny MLP I showed you, there are 25 parameters. So that corresponds to roughly 18 connections and 7 biases that we have to set. So we can't vary all of them at the same time. Like that's not a good idea. The tiny MLP I showed you has 25 parameters. The demo that I'll be doing, if time permits, will have 93 parameters, and loss will be 94 dimensional. The transformer that we'll get to will have 125 million parameters, and GPT-4o, that I'm sure you're aware of, has 200 billion parameters. So big loss. You can't really plot that here because you'll need 2 million dimensions to do that. So we do this by, how do we calculate our loss? More importantly, how do we tune our parameters to minimize loss if we can't really plot the loss and test it for every possible value of the parameter, which is a horrendously infeasible idea. Well, we'd look at optimization techniques. And if you have experience with optimization, you'll know exactly what I'm talking about in the next slides. If you don't worry. Optimization refers to finding the extrema, the maxima, or the minima of a function. So in the case of our loss, we try to find the minimum loss. So we try to find the combination of parameters that gives us the minimum loss. And finding the minima gives us the model optimum parameters. How do we do this? Well, it's a good technique, right? Like in theory, it's a good idea. If we can just find the minima of the loss function, then we get the optimal model parameters, which is the model parameters that we want. We do this using gradient descent. Now, gradient descent is one of the most commonly used techniques in optimization, and it's one of the most powerful because of how simple it is. Now, imagine if this, right? Sorry, 0 means it's 100% accurate. And how would we be able to visually represent a GPT-4o loss graph? I don't think you can represent a GPT-4o loss graph, honestly. It's because 200 billion dimensions. And yes, 0 means if 100% accurate, correct. Yes. So that's how loss works. A loss value of 1 would mean that it's not very good. A loss value of 0 would mean it's really good. Sometimes loss values can take values below 0. And that's depending on the loss function you use, but that's beyond the scope of this class. I'm not here to talk about machine learning. I'm talking about deep learning in particular. So if you have questions, ask during the break. I'll be more than happy to answer them there. Okay, gradient descent. So if we have a loss function, assume that the red curve is a loss function and the parameter we are varying is between like minus 1.5 to 1.5, then I can just test many values of the parameter. Like I'm testing for my demo, I'm testing 5 values of the parameter. And I want you to think of gradient descent as, again, this is a really popular analogy. Think of it like a ball rolling down a hill. And a ball rolling down a hill will always choose the direction of steepest fall. That's where it wants to go the fastest. And you do this by, I'll just run the animation. I think that should be self-explanatory. If I can I run an animation here? It's not good. I see. Yep, there we go. So you're trying to increase or decrease the parameter value in the direction of greatest change. So we started at a certain parameter range and we went all the way down to wherever we found we could go without going further downwards. So we try going in the direction of greatest change and we stop, we find the direction of the greatest change again, and we keep doing this until we are at a minimum. So we try doing this until we can't go down any further, and that's our optimal quote unquote value of a parameter. So it's the best value of the parameter given the starting conditions. So gradient descent for formally is a blanket technique for unconstrained parameter optimization given an initial estimate. So it's a ball rolling down a hill. For a loss function and an initial guess, you update it using steps and cycles. So each step you update it with the direction of greatest change, which we represent by the gradient. And the gradient is represented by the inverted delta sign. Also, for some reason, I can't see the Zoom chat. So if you have a question, just, I guess, briefly unmute and let me know, and I'll be happy to check. Okay, I'm not sure why that is, to be honest. I'm sorry. So that's gradient descent. So we use that to find the minimum of our loss function. If you don't understand it, it's fine. It's not really relevant to deep learning in particular, but it is the cornerstone of machine learning. So yeah, there's a million and one videos on that. I think 3 Blue 1 Brown has a really good video on that. Just, yeah, go for that. Watch that. So the training process for our MLP. So we pass our training data through the neural network. We compare the predictions of that neural network, so the output at the final layer with expected results. We adjust our weights and biases to reduce the discrepancy between the two at each step. We do this by gradient descent. And we repeat steps 1 to 3 as many times until we get what we want. So we get the accuracy that we want. MLPs in action. Okay. Before that, does anyone have any questions? Okay. Let's see. Do you have questions? There are questions. Are there other ways to minimize loss? Yes. Which one's the best one? There's no best one particularly. Gradient descent is usually used, or like modifications to gradient descent. And there's also something called Newton's algorithm for incremental decrease. So that uses the second derivative. So it doesn't use the first derivative as gradient descent does. And it has its benefits, it has its drawbacks. Again, there's a fundamental problem with finding the minima in that it's really hard to find the global minima for anything. So if you want to discuss that more, I'll be happy to do that in the break, but I don't think I have the time to discuss that right now. Okay, so MLPs, really simple to code up. I'm going to be using the iris dataset, which is essentially a bunch of flowers. If and it has each flower has 4 parameters. So it has the length, breadth, petal width, petal height, or something like that. And yeah, based on that, we have to predict whether the flower is a setosa flower, a versicolor flower, or a virginica flower. So we have 4 inputs, which are physical characteristics of the flower, and we have 3 possible options for the output. So let's first we load in our data set. This honestly, yeah, if you know what you're doing, you can do this via ChatGPT. And let's build our neural model. So we want to have, let's say, we want to have our model sequential. So we want to pass our data from left to right. And let's begin with a network of linear neurons. Now, a linear neuron is essentially the same thing as the same concept and the same diagram as what I described in the slides. So that shouldn't be anything new. It's honestly just the same thing. It's fully connected. It takes in 4 inputs, and let's say I want my model to be 6. I should have 6 hidden layers. Then I pass it through an activation function. So again, as I think someone else was pointing it out, it could be anything. So why am I getting 2 cursors? Yeah, it could be anything. Not sure why I'm getting 2 cursors though. Which Python library is the best for doing deep learning? I currently use TensorFlow and scikit-learn. Is there anything better? No, I think those are industry standard. You can also use PyTorch, which is what I use because, yeah, like that's just personal preference at that point, but they're all equally powerful. And yeah, okay. I'm not sure why the demo is not working, but that's unfortunate. I see. Okay. So we have a linear model, then we pass it through an activation function. Then we have our hidden layer of 6 neurons. So we have another linear model that takes in that has 6 hidden neurons and outputs to, let's say, another hidden layer of 6 neurons. We pass this through an activation function. We pass it and the activation function, following which we pass it through our final layer, which takes in an input of six neurons from the hidden layer and outputs to 3, which correspond to our 3 possible options for flowers. And finally, we pass this through an activation. So the thing I'm trying to show here is we pass in our data through consequent layers of linear networks. And I'm not sure why I keep getting cursors like that. This doesn't usually happen. Right. So yeah, the point is that I'm taking an input of 4, then I pass in as many layers as I want. And finally, I get an output that I pass through a sigmoid layer. So at each level, what I'm doing is I'm passing my data through a linear layer, and I'm passing that through an activation function. So the sigmoid in this case. And if I run this to train, it's really fast. The training is essentially we take a loss function, we do gradient descent using libraries, and yeah, if at each level we take a step along the optimizer, so we make our ball roll down the hill, and we make our loss function incrementally better. Finally, we evaluate on the test set, so we try to see how many we got correct. Well, that's not right. That's unfortunate. Right, at any rate, that was a colossal failure, my bad. Still, the point is that you're taking inputs through linear layers, you're passing them through activation functions, passing them through linear layers, passing them through activation functions, and so on and so forth, until you get an output and you get a decrease in the loss. And you should see training loss decrease over time. And that's what would imply a successful model. At any rate, that was mildly unfortunate. Sorry about that. But yeah, I think that's yeah. So okay, I have 2 questions here. How does one choose hyperparameters and layers? Is there a golden layout for model structure? Not really. You can pick anything you want, really. Like for the most part, MLPs are fairly robust as long as you go like 2 layers or above. It's fairly safe. What does epoch mean? Epoch is just a fancy term for step, so iteration. So if I'm at like my first epoch, that means that I've done my gradient descent once. If I'm at the 500th epoch, it means I've done it 500 times. So yeah, epoch it literally just means era or age in English. So yeah, cool. So we're at the halfway point of the class. I think good time to take a break. Go grab some water, do your thing, just relax. And if you have any questions, put them in the chat. Could be about this, could be about anything. So yeah. Why is the graph not going linearly down? What's the reason for the slopes? Well, the way gradient descent works is you get really fast changes really early, because if you're in a bad place, you'll have a very steep descent. And that steep descent would give you great increases in loss, great increase in performance, because you'll have great decreases in loss. But then as you go near the optimum, the slope becomes less, so you're taking smaller and smaller steps for the parameter each time. So you're trying to essentially tune your parameter by a certain amount, and that keeps going smaller and smaller. When you want us to be back from break, for me, it's 11:05 Pacific time, so maybe 5 minutes. So 10 past the hour. Does this make it impossible to reach? I'll just put it in the chat, sorry. Does it make it impossible to reach a loss of 0? No, actually, you can reach. So, if there is a global optimum, the gradient descent will reach that at some point if you tune your parameters correctly. And there's a whole field of study dedicated to that, what parameters you should be tuning. There's something called alpha values in the gradient descent. If you tune that correctly, if it's small enough, then you will always reach the optimum. Going to take up DSAI in I'm going to take up DSAI in undergrad. As a senior, what would be your suggestions and what classes and topics in undergrad do I need to focus on or complete in high school to get a head start in undergrad? I'm assuming DSAI is data science and artificial intelligence. Please correct me if I'm wrong. Okay, cool. Um, as a high schooler, honestly, nothing. I didn't do any AI or ML in high school. Like, whatever you're doing should be of your own passion, whatever you find interesting, or whatever you find a use in real life, just go for that, apply AI there. In college, I think in general, if you're actually in high school, you should be taking foundations. So you should be taking linear algebra, and you should be taking multivariable calculus if that's offered, or vector calculus or any of the sort. And you should be self-studying that. There's really good resources online for 3 Blue 1 Brown, and the Ben Eater has some really good places. I can recommend a few. So yeah, go for that, read that. It's like, trust me, it'll help you so much when you actually get to the machine learning part, because if you understand the model, then essentially half the battle is won. Um, okay, I had two quick questions on gradient descent. When using it for optimization, you mentioned that you wouldn't need to plot all the parameters, but to get the optimization function, wouldn't you need to have a loss function with all the parameters to take its derivative? What if you're in a function where the local minimum is much higher than the actual minimum, that the ball gets stuck in the local minima? Okay, so these are two questions. The first one is, through some clever tricks regarding discrete arithmetic, you don't actually have to have the full function with you. You can just evaluate the gradient at a specific point. This you can do via Taylor expansion if you're aware of that. And taking the gradient of a function at a certain point when the whole function is not known is actually very well known and is very well adapted. So to answer your question, a bit beyond the scope of what I can teach today, because that in itself is an hour lecture. But yeah, there are ways. Secondly, when you're stuck in a local minimum, what you've hit on is one of the biggest problems in modern machine learning. And that is that it's really hard to find the global minimum, and it's really easy to get stuck in a local minimum. How can you avoid that? Well, there are techniques. They're called Monte Carlo sampling algorithms. So I'm going to throw names like of algorithms, but I don't think there's a point to that. One of the simplest ways to avoid that is to just test a large variety of initial values for the parameter. So if you think your parameter is kind of going to be in the like 0 to 100 range, then I'm going to try like 10,000 values of the parameter. 990 of them can get stuck in the local minimum, but there's a high chance that 10 of those initial values will converge to the global minimum. So yeah, if you just do a blanket of all parameters, then yeah, that should save you. Computationally, that's a lot more expensive. But that's a trade-off that, again, you as an ML engineer will have to make. So you'll have to decide that. Thurv has asked, is Python the best language for AI, or are there any other languages that I used? There's a lot of coding in JavaScript for interactive web frameworks if you want to make your ML model interactive with people, publish it on the net. So that's fairly popular. Are there any other languages? C++ is used at the low level, but only if you know what you're doing, which, like what I'm teaching you, you should be extremely comfortable transcribing word for word because there aren't any libraries in C++. But if you can get there, then it has an exponential increase in speed. Um, is there any other coding? I think that's pretty much it. Uh, Julia is a good language. Yeah, Julia is, yeah, I would agree. Yeah, Julia are, so statistical languages are fairly popular for ML. The only problem with them is scale. And Python has so much infrastructure that's designed for scale, so you can train multi-billion value parameters on there. So yeah, like Julia and R are really good, but and definitely like good for your purposes and mine. But on an industrial level, you might not see them as much because they're primarily scientific computing. To understand more of the math behind this, do you recommend any specific online course I can look into? Andre Karpathy has a really good course where where he teaches MLPs from scratch, transformers from scratch. I would recommend that. Uh, he's pretty I think he's probably the gold standard because he's invented a lot of these concepts and he's the founder for a lot of these ideas. So he's one of the founders for what I'm about to teach now in convolutional neural networks. Okay, so is everyone back? Give me a thumbs up virtually or otherwise. Okay, good. I'm impressed. There's a lot of people are still paying attention. I was kind of thinking that you'll tune out by this point. Okay, good. Let's move on to part two of our course. So for now, this was the basics. And by basics, I don't mean this was easy. I just mean that this is something that you will be exposed to as you start deep learning. Now we'll be going on to some higher level concepts, which means I won't be going into the details, the nitty-gritties as much, but I will go over a high level intuition. So I want you to understand what these models are doing rather than go through what each neuron is doing in those models. Right. Uh, okay. So let's let's jump right into it. Just a second. Can you see my screen? Great. Break. CNNs, that's part two. And let's talk about one fundamental issue with MLPs. There's many, but let's talk about one. They can't capture certain intricacies of data. If I have not all my data can neatly fit into this one-dimensional input layer that I have, that's not really good. For example, I found this picture of a cool car. If I pass this into my machine learning model, you'll see an issue that comes up really fast. But first, I want to highlight something to you, something I'm sure you haven't noticed. This is a two-dimensional picture. It has an x-axis and a y-axis. Now, if you're seeing this, I'm sure you're shocked because, yeah, there's no way this car is two-dimensional, right? Well, if you were a machine learning, you actually would be shocked because the way this goes into a machine learning model is like this. Now, the car itself has 2 million inputs, by the way. So these arrows you're seeing over here, there'll be roughly 6 million of them. So again, too many inputs. And if you notice keenly, this does not look like a car. And I'm sure that while I was seeing the picture of the car, there was some information in this picture that made me realize, oh, this is a car. But if I look at this picture, then I don't really see it. So there is something that we have lost when we are converting this two-dimensional image into one dimension. So if we're converting this to one dimension, we have lost local spatiality. We have lost things that connect neurons, that connect pixels across dimensions. And that's not good because that is significant information. So to solve that problem, let's talk about the CNN. The CNN is a convolutional neural network. And what I want you to imagine here is instead of having an MLP, consider taking this particular car as a newspaper. And imagine you're reading a newspaper with a magnifying glass. Now, I pass the glass through the whole paper. So the way I do that would be, if I could run this thing, that would be very good. I do apologize for that, by the way. I'm very technologically challenged. At any rate, I think we can skip past that, honestly. Shouldn't be too bad. So yeah, imagine reading a newspaper with a magnifying glass and pass the glass through the whole paper. And now imagine if my glass can make the edges very sharp. And that should look something like this. If I have an image and I pass a magnifying glass through the image, and For each pixel, I compute some filter that I'm calling a Sobel filter here. I compute some filter that allows me to determine edges of a car. Somehow I know this filter, assume I know this through some magic. Then yeah, like this is really good because this allows me to get rid of all this noise, like all the stuff that I don't really care about, and only worry about the car, which I can clearly see with the edges. So I save some patterns over here. I understand what makes a car, and part of that is the edges of the car. So I've captured this information in a model while disregarding everything else. That's edge detection, and that's the principle behind convolutional neural networks. The structure of a CNN. We have an image, we do edge detection, we do dimensionality reduction, then we do edge detection, and then we do dimensionality reduction. We pass that through an MLP and we have an output. Simple, right? I think that's my job done. There's no more explanation needed, I think. We are perfectly good with this. No? Okay. I'll explain this a bit further. The first step should be simple. We have an image, and then we pass it through a convolutional layer, which is what we described earlier. So the Sobel filtering, what it's doing right now is it's doing a convolution. The exact details of what is a convolution mathematically, you do not have to know. But the key point here is that it's creating something that detects edges. Pooling and dimensionality reduction is an important concept that I'll get to now. Once we have detected our edges, I claim to you that we need to reduce the size of the image. We need to make it smaller. Why? Well, for one, smaller image reduces overfitting. So if I have, in this image, you can see that even the highway has some reasonably good edges detected. So you can see that there's edges over here, there's edges over here, but we don't really care about that. We only care about our car. But if we reduce this image, and if we make it smaller, if we cut out significant parts of it, then I get I get a reduced overfitting. So I get fewer activations, I get a smaller model capacity, and a less chance of memorizing random noise. Secondly, lowers compute costs, obviously a good thing, because trust me, you don't want to see how much GPU I've consumed in the past year. It suppresses noise, and the way it does that is if I have all this noise, I have these trees in the background, this stripy line over here. I don't want that. It suppresses them, and if I reduce the dimensionality of this, then it suppresses the noise. It suppresses things uniformly, and it only keeps the most important features. And finally, it expands receptive fields efficiently. So if I downsample it, what's happening here is if I make this image smaller, then each neuron in the subsequent layer gets twice the amount of information that it would have gotten. So I'm boosting each neuron by a factor of 2 if I reduce the image by a factor of half. Does that make sense? Okay, I'm going to take that as a yes. How do we do that? With pooling. And since I apparently cannot play video, sorry, that's you're gonna have to deal with my explanation. I do apologize. But essentially what that means is when I pass that red little box, what I'm doing is I'm trying to calculate the maximum pixel value of all the pixels in that box. And I output that as an input to my neuron. For max pooling, I'm trying to find the maximum value. For average pooling, I'm trying to find the average value of all the pixels in that red block. And what that means is that if I'm doing max pooling, then I emphasize the strongest features. And what does that mean? In this picture, I'm emphasizing the edges of the car over all the other things, which are noise. So I'm emphasizing the strongest features. Average pooling outputs the mean pixel value, and it preserves the original texture and the brightness so that we don't only have the final, we don't only have the car, because we should also have some data that is malformed so that the model learns what it's doing. So again, no picture. Let's talk about this. Let's talk about what each layer is doing. Putting it all together. So the anatomy of a CNN. The first thing is an input. So we have the input image. And the input image is some height times width. And why do we do that? Because it preserves spatial and color structure. So we don't flatten our image, we keep it in 2 dimensions, and that preserves spatial structure, it prevents color structure, and such and such. The second layer is convolution and activation. And what it does is it has learnable filters that scans local patches in each image. And that detects edges, it detects textures, it detects patterns with few parameters. And it allows us to capture what it means to be a 2-dimensional image. Anushka asked, by max pixel value, is it the highest RGB value? Okay, that's interesting because the visual depiction I'll be doing for a CNN, and that's through a website, so it should not break, uh, will do an RGB, and it's slightly more complex with an RGB than a black and white, which is why I've shown a black and white here. Because black and white only has one, it has like each pixel has a value from 0 to 1. So you only have one number that you're dealing with. Black and white, RGB has 3 numbers that you're dealing with, which means you need to split the image into 3 channels where you deal with one number at a time, one channel at a time. So you deal with the red part at a time, the green part at a time, and blue part at the time. So yes, it's slightly more complex there, and we'll get to that. I'll explain that when we get there. Yeah. Okay, so we have convolution and activation. Then to detect edges, then we do pooling, where we downsample or reduce dimensionality. Why do we do that? Because we reduce the feature map size, which means low computation memory, and it improves robustness to small noises. And we do this process, convolution and pooling, multiple times because the early blocks learn simple local features, and deeper blocks compose those into higher order representations. So if I do pooling once again, if I do pooling and then I do convolutional layer, then pooling and then convolution, and so on and so forth, I can learn increasingly complex layers. Finally, once I'm done with this, I flatten my data because now I have a full information of what the 2D structure of the image was. I pass that through an MLP, which is now rich with the features that we've just described. It has an output, and that's the output that we're looking for, prediction. Okay, let's do a visual depiction of a full CNN, and this has the color that you were talking about. There's someone in the waiting room. Okay, now I just looked at the definition of bias while I was talking there. Okay, so this is a depiction of a CNN that has been made by someone much smarter than me. But more importantly, it has the full color image. So what we're doing is we take an image, let's say an image of a cup, and we're trying to predict that this image is indeed a cup. So it tells us that the image that we've put in is indeed an espresso, indicated by the long line. And how do we do that? Well, it's a colored image, so it has RGB channels, red, green, and blue. And each pixel has a red, green, and blue value. We split that into the red channel, the green channel, and the blue channel. So each channel gets one specific convolutional layer. Then we pass it through a convolutional layer. We pass it through another convolutional layer. We pass it through a pooling layer. We pass it through another convolutional layer. So this corresponds to our idea of passing the input through multiple convolutional and pooling layers so that each layer learns more and more local structures. And once we do that, we pass it through pool, and then we do convolution, we do pooling, and in the middle, we do linear unit activation, and that's our MLP model. ReLU it's not an optimizer, it's an activation function. So it's kind of like sigmoid. It's kind of like sigmoid activation. So this is what a sigmoid looks like. And a ReLU looks like this. So it gives an output of 0 until a certain point, and after which it starts giving a linear output. It's called a rectified linear unit. Yes. Okay, let's get back to the slides. What exactly is a convolutional layer? Yep, I didn't explain that very well. Good catch. A convolutional layer is, one second. Okay. The right time a computer decides to break. That's lovely. Okay. So a convolutional layer is a layer that essentially takes an image, and at each point in the image, it runs a filter. What does that mean? It takes, let's say, this box, and it does something called a convolution. And what that means is it multiplies all the pixels. So it takes this pixel matrix over here. So this is a matrix. It takes that and it calculates the multiplication of that pixel matrix. For example, if my pixel matrix is, let's say, 0, 1, 1, 0, and my filter is another matrix like 1, 0, 0, 1, then I do a convolution operation. And a convolution operation on this matrix would give me an output value that would correspond to this box over here. And then I do it for the next box over here, which would give me an output of the box here. Then I would do it for the next box, and that would give me a box here. So I keep going, I keep making my window shift a bit to the right, and I do a convolution with this set filter. So this is a certain filter that I found, or I've given to the model, and it keeps multiplying this filter, it keeps convolving this filter with the pixel values in the matrix and creating outputs there. If that makes any sense. Okay, like element-wise multiplication, yes. Which is better, or does it differ based on task? I'm not sure what you're referring to by which. So why would you need to multiply the matrix? So, okay, so I'll get the question wise. Okay. Activation functions. Okay. Neither of is particularly better. There's different reasonings for both. So it translates the entire image pixel into a giant matrix and then feeds it into the MLP. It translates, yes, in a sense, yes. So once I do my convolution, I get an image I get a transformed image that is filtered, that is far better than the original image because it has the relevant parts of that image marked out. So yes, it does that. It decreases the dimension. It does the convolution again. It decreases the dimension again, and then finally passes that into the MLP. So why would you need to multiply the matrix? It's not a multiplication per se. I misspoke there. It's a convolution. And the convolution is what allows us to obtain those edge filters. So for example, the Sobel filter is a specific matrix that was found by a person called Sobel that calculates that when applied to an image would amplify small lines over large swaths of the same color. So is the filter kind of analogous to a weight in an MLP? Yes, it is. One would learn a filter the same way that one would learn a weight. That's certainly possible. In many CNNs, we pass in the filter. For example, like the filter I just gave you, Sobel filtering. I just realized I don't have my screen shared. Um, yeah. So the filter I just gave you here, Sobel filtering, that gives you the same concept. So it's analogous to a weight, but it's provided. So we provide that filter. But yes, you could learn the filter as well by the image, by the training. Yeah. Any other questions? So the CNN finds the most important relevant parts of the image, and the model focuses more on the right stuff instead of the noise. Yes, that's exactly correct. So how it finds the right stuff is through the filtering, and how it focuses on the right stuff is through the dimensionality reduction, so through the pooling. And we keep doing that until it hones in on the exact most compact information that you can provide to the MLP that captures all the essence of a two-dimensional image with local spatiality. Okay, so we have visual depiction of a full CNN. And yeah, this was a relatively short section because CNNs aren't that commonly used nowadays. They've made a resurgence, but they aren't that used nowadays. Is there a way to do this for 3D things? Yes, absolutely. And there are many techniques to do this for n-dimensional tensors, which are essentially 4D, 5D, 6D concepts. So yes, you can do it objectively, like it's not that difficult. Cool. Not gonna take a break here, I think, because we're running short on time. But yeah, like I didn't make this a long section because again, CNNs were really good back when they were introduced through AlexNet in 2012. They fell off a little bit when transformers were introduced, but now they're making a resurgence again through some dynamic filtering processes. So again, really cool work. I would recommend, again, Karpathy has good videos on CNN, and yeah, do check it out. Okay, we move on to transformers now. Not the robots, but just as smart. Transformers are perhaps the most important invention of generative AI and machine learning in the past decade. So, to introduce the idea of transformers, I'm going to give you a conundrum. This is English, and English is a weird language in that I can put one word at 4 different places in a sentence, and it'll have 4 different meanings. Only I love Transformers, I only love Transformers, I love only Transformers, I love Transformers only. Each of these sentences has a different meaning. And if I asked you to read it in context, you can see it, you know the meanings, and interpret it dynamically. But if I give this sentence to a machine without teaching it what it meant, without putting it in the training system, how does it know? Can it know what the context is? And how the meaning of the sentence changes just by intersposing like 2 different words? Turns out you can, and that's the premise for a transformer. This is a famous paper. It's a landmark paper in 2017 by Google that introduces the concept of self-attention. And attention is the single most important part of a transformer. It's what separates a transformer from any other machine learning model. And we'll discuss attention in detail shortly, but it's the concept of attention that is significant. And it was originally used for translation, which is a surprisingly difficult task because languages have different contexts. And if you can understand what a word means in context, you've essentially done half the translation, because then you can translate to the right word in that context. And yeah, it revamped the Gen AI landscape. So we had the problem, but let's talk about formalizing how we motivate a transformer. If I asked you to put this sentence deep learning dash in Google autocomplete or like WhatsApp autocomplete, what's the best continuation? Option A, B, C, or D? Deep learning amazing, deep learning deep learning revolutionary, deep learning is. D, thank you. Yes, that's a good answer. Good answer. Uh, correct, you're right. That's how Gen AI works. Yes, I'm building up to that, actually. So the best continuation is is. Now, I'm going to do something revolutionary. I'm going to append is to the sentence, and I'm going to ask you the same question again. Deep learning is dash. Finish this new sentence. What's the best continuation? Is it amazing? Is revolutionary? Is a? now the answer is not so clear cut because it could be anything, like we don't know the context, right? But if I keep asking what's the next word, so if I have this phrase, what's the word after this? You have generative AI is generating new content based on some initial seed. So the seed here was deep learning, and the generative AI part is the part where I'm asking, what should I put after this? So let's go back to my initial conundrum of what's the good word here, and let's revisit that. Language is data, and the golden rule that I've discussed before says that everything is data. So I convert words to numbers, I tokenize them is the official parlance, and I do that via a tokenizer. And that means that if I have a certain phrase, I can convert that to numbers. And this is the actual mapping of I love deep learning to numbers in GPT-2, which is the model that we'll be using today. By itself, this doesn't solve anything though. Like so far, we've just converted deep learning into a bunch of numbers, which doesn't tell me anything. But it does allow us to pass input into the model. Now, a good question would be, how does this tokenization work? How do you convert language into numbers? Well, GPT there's so many different ways. The first one would just be simple, convert each word into a specific number. That's good. Like for example, I assign I the same value of like, let's say 40. And no matter wherever I see I always assign it the value of 40. And that's a good idea, but the problem is that, again, words have different contexts. So for example, learning here has a different context than in some other context. Like for example, if I say I'm learning to cook versus I say I love deep learning, there's two different contexts there. And that means that we should be having two different maps for the vector. So ChatGPT does it by encoding UTF-8, and it does byte pair encoding. You can look that up if you want. So it does pairing by bytes. It learns single bytes. So someone back when they were training ChatGPT trained the model on pairing single byte simple. So they taught the model how to do like tokenizing 50,000 times. And then they used that to create more and more inputs, more and more examples, and they trained, essentially the model trained itself. Okay, that's not really relevant though for our purposes. We can just assume that we have a tokenization and that we can convert words into numbers. Because no matter how you do it, there is a way, and that way is what's important. It's not how you do it exactly. So by itself doesn't solve the context problem because we still don't really know what each word means. Like these numbers don't mean anything to me. But we have an input now. So we can pass this into a model. And here we introduce the concept of attention because we need to solve this context problem. We need to know what each word means in context. So assume you're reading a book and you keep every past word that you've read in your memory. And that's kind of how reading works, where, like, let's say you read a sentence, you'll be like, I've read until the fifth word. Well, I know what the four words before were, which is how I'm able to deduce the meaning of the fifth word. Now, if I encounter a new word, I generate a mental query that scans my memory of the words I've read before, and I ask, how useful is what I have read in helping me decipher this word? So in context, I could be thinking about a certain word and be like, the past 10 words that I've read, are any of them useful in helping me figure out what this word means? And surely some words are relevant, some words are not, right? So I give each word a score based on how helpful it is for understanding the current word. Then I pull together those words, I add them up, weighted by their scores, to form a single context summary. And that single context summary is what guides my guess for the next word. So I'm at the current word. I've summarized everything before that word to create a summary of that word. And then I use that to create my guess for the next word. If that's not clear, let's do an example. This is a famous sentence in English. The quick brown fox jumps over the lazy dog. It uses all 26 alphabets. It's fairly popular. Now, what if I've read the sentence till over? So I've read the quick brown fox jumps, and now I'm at the word over. I'm going to look over each word and determine whether it's relevant for me to understand what context the word over is used for. Because over has many meanings. Over could be an adjective, it could be a preposition, it could be a noun. There's so many ways you can use over. Now, let's go through each word. The, not that relevant. There's not much relevance between the and over. Quick, not really. Like, they're not that relevant. Brown is also not relevant. Fox is kind of relevant because it says that the action word over is being done by the fox. So it's sort of relevant, like heuristically we would say that. Jumps is very relevant because it identifies the fact that over here is a preposition. If you had some other use of the word over, for example, the day is already over, then that would not be a preposition. But because you have the word jumps over here, you can identify the meaning of this word to be a preposition, to be above something, to be over. Let's rank them. So the has low relevance, quick has low relevance, brown has low relevance, fox is kind of relevant because it's the subject, and jumps has high relevance. That's the context for understanding what this word over means. Now that we've identified that the word over is a preposition, well, we can just use the next word then. Like we can just find the next word. Because now we know the meaning of the word over, we can assign it the right token. And then once we have the right token, we can just pass our data through an MLP and use one of the MLPs, one of like thousands of training inputs to come up with our next word. Formalism. Now, this is optional. You don't have to understand this, but if you do, pretty good, honestly. Okay, in an attention layer, so we do this, we call this attention, and in an attention layer, there are 3 pre-trained matrices. This is where the word pre-trained comes from. So we train these matrices on vast swaths of data that we have collected and manually sifted through. That's what ChatGPT did before it released ChatGPT 3. Now, for a current word, X, the WQ, the matrix Q, asks the question of, is any word in what I have read relevant? That's the question. K presents what prior words have to offer our current word. So K tells K for a specific word tells us that, yes, like this is what I can help you. This is how I can help you in determining what the meaning of this current word is. And V represents the actual information we need, which is context differences. So it represents the difference between what we have, the meaning of the word, and what we need, which is the actual meaning, which again is pre-trained. So the model has a pretty good idea of what it wants. It just needs to confirm that. So to ask the question, we compute Q, the question, which we take the matrix W, which is a pre-trained matrix, which is the same for any input, any model whatsoever. We take this matrix, we multiply it by X to get a certain question. So we frame our question like this. Then we check the prior word. So we compute, to check what each prior word can offer, we compute K, which is K, what prior words have to author. And for each prior word, we multiply the matrix WK with the prior word. Then we calculate relevance, which is through the dot product of the question times the what each word has to offer, and on which we then apply activation, which is how we make a decision for the next word. And then finally, we weight the relevance with the information that we need, and that gives us something that we can pass into our MLP that is context aware. What that means is we know what the meaning of the word is in that context. And that's important because once we have that, the MLP can just run through its data. And yeah, that's pretty much it. Attention. It's a contextual lens which computes which prior tokens matter most for each word. The MLP is a decision maker, and it takes in this data from the attention, and a small MLP transforms the attended context into the next word prediction. And again, to improve the system, we can stack at many attention blocks. So we can have each attention block with its pre-trained W matrices. focus on different things, focus on different relationships. So parallel blocks capture diverse relationships, and then we can have an MLP and an attention that stack layers that build deep and comprehensive context. So that's a transformer. I'm hoping I can get this. Let's see, we have roughly 5 to 10 minutes. I should be able to, if I try. Uh, right. So the model I'll be using right now is what we call it's the GPT-2 model. So it's the last open source model that ChatGPT came out with, or OpenAI came out with. And it's one of the most popular scientific models because it gives us huge insight into what each model means and what a model is doing. So I have a model and I have a tokenizer which creates tokens. I have my prompt, which is I love deep learning. And if I run this, oops, I'm not imported the model yet. And the model is huge. Again, it has 105 million weights and parameters. So it does take some time. And given that the size of the model is significant, the computation is also, if it weren't pre-trained, the computation would take an enormous amount of time. But as you can see, we have our prompt and we have tokenized it into a tensor, which is a 4-dimensional tensor. So it has one number for each word. So 40 stands for I, 1842 stands for love, so on and so forth for deep and learning. Now, from here, let's find the next token. And for that, we just pass in our model, we just pass in the input, the tokenized input, into our model, and we get an output. And finally, we show the probabilities for the top 10 words. And the top 10 words are a full stop, a comma, an and, because, for, and so on and so forth. So what this means is the most likely continuation of I love deep learning will be a full stop, which kind of makes sense because it's a full sentence in of itself. Now, what if I give it an open-ended prompt? Now, this is a small model, so let's talk about what that means. At each level, I'm providing the next most likely word and appending that here. So deep learning is a new approach to learning. Full stop. That's nice. But again, it's not very useful, but it is what is doing is very clear. It appends a word at the end of each prompt, and we use the same prompt to start the cycle again. How can I replicate this program on my computer? I'll be putting the source code and the presentation on on the Splash website, so you should be able to copy it down. Otherwise, it's fairly easy. You just download it from you download GPT-2 from the internet. Hugging Face has it, and yeah, just play around with that and get ChatGPT to help you. It's really straightforward. So all it's doing at each point is identifying the next word, and is doing it via attention blocks. It's doing it via context windows. So that's a transformer, and that's the cornerstone of deep learning today. I don't think I have anything else for you. So synthesis, I'll just end with that. Deep learning is everywhere. It's honestly the most prevalent form of learning today. And I gave a high-level overview skimming over the math. And if you're interested in that, it's a lot of fun. I promise you that. It requires some knowledge of linear algebra, multivariable calculus, and it's really fun once you get into it. That being said, you don't have to reinvent the wheel. There are tools, there are libraries that exist that make your life easier. And look for those whenever you're doing your own projects. Look for those whenever you're stuck, because again, people have spent years of their lives dedicated to perfecting them. So don't reinvent the wheel and use them ethically and sustainably. You should have an idea of what's going on. behind the scenes, but don't get carried away and don't exploit it for needless gain. Good question. What's the difference between machine learning and deep learning? Machine learning is a much broader category that deals with more than just neural networks. So deep learning is exclusively to do with neural networks. So today, as you noticed, we only talked about that. Machine learning also introduces concepts such as unsupervised learning through like mathematical functions, through decision trees, through like clustering. There's many different ideas in machine learning that you can cover that don't fall within the realm of deep learning, which is just neural networks. Any other questions? What will happen if two or more options for the next word in the demo have the same percentage? Tie breaks. So normally what happens is in advanced models, you don't even pick the likeliest word. You just have a good chance of picking it. You can pick any of the words that come up in the top 10 or like top 20 or whatever it is based on some random chance. This is why if you give the same output to ChatGPT, it'll give you two different results if you run it two different times. So if they'd have the same probability, then we pick one of them at random. That's the tie-breaking scheme. And yeah, we just go from there. Any other questions? To learn computer vision, do you recommend starting with learning CNNs, or is there a more advanced current architecture that I should focus on learning? CNNs are a good architecture. They're really robust, they're really strong. The only architecture I can think of that consistently outperforms them is vision transformers, which is again, they are pre-trained, so they're outside the scope of what you and I can do on our local laptops in training. So yes, I would go with CNNs. They're really good, really powerful. And like I said before, good strides have been made with CNNs recently that can even outperform transformers. So I would go with that. Cool. Thank you. Thank you for being here. Anyone else? Oh, also one more thing. I think there's a feedback form. Please do fill that up. I'll just post that. I think there should be one. So before you go, just fill that up. And yeah, like I'll be forcing everyone out by 11:57, 11:58, because the next class is also in this room. But yeah, like if it was a genuine pleasure to have you here, and thank you.